I said in our electromagnetic waves video that we were going to look in a bit more detail at reflection, refraction and diffraction. So I'm going to start with refraction. Now I hope that most of what I'm going to say should just be a recap from what you've learned at GCSE. I also know that you've probably forgotten a lot of this, so you may just want to refresh your memories a little bit. So refraction, hopefully we know that refraction is when light changes direction after passing through a boundary. And the important thing about what happens at this boundary is that the speed of the wave changes. So in the example I've got in here, you can see that we're showing the speed of it by the spacing of the waves here. So it's going faster in the first medium and then slower in the second medium. And what this causes it to do is one side of the wave starts to slow down before the other side. So it's kind of like if you're driving along in a car and one of the tyres hits sand and the other two are still on, the other side is still on the road. The wheels on the road are going to go faster than the wheels on the sand, which is going to cause the car to turn, and that's what you can see happening here. Now it says here that the change of speed usually, but not always, results in a change of direction. That is because if I hit it straight on at 90 degrees, so if my wave was travelling straight like this, it'll change speed when it hits the boundary, but the whole width of the wave will change speed at the same time, so it'll just keep going on in a straight line. It will just have slowed down. So that's the exception. So let's just have a little look. Now, you've probably studied this earlier in GCSE with perspex or glass blocks. So you shine the light ray in, and then we look to see where it goes. So if I'm going from air into glass or perspex, I'm going from a less dense to a more dense material. And I'm particularly interested in its optical properties, so I'd say it was a more optically dense material that we're moving towards. So this here is my light ray, which please note is a straight line and has an arrow on it. And I then put in this imaginary line, which is just a construction line, which is called the normal. And the normal is always at 90 degrees to the surface that we're interested in. So the angle at which I'm sending the light in, we would always measure from the normal to the light ray. So whenever we're measuring an angle to do with a light ray, you want to measure from the normal to the light ray. And because this is the incident ray, this is the angle of incidence. When it hits the glass, one side is going to slow down, the side that hits first, and that's going to change the direction of the light ray. Now, here it's now in a slightly different position, and I've now got an angle on this side, which is between the normal and the angle. Since this is now the refracted ray, this is the angle of refraction. Same would happen if I brought it in at a different angle, so that would be my angle of incidence, that would be my angle of refraction. Now, thing to note, in this situation where I'm going from less dense to more dense, the light ray is moving towards the normal. And very importantly, the angle of refraction is less than the angle of incidence. Those two things are telling you the same piece of information. But if you are asked to sketch one of these, you need to make sure that you show which way the light ray moves, its path moves, and we do that by thinking, is it going from a less dense to a more dense, or vice versa. So this would be going into the block. We could also be coming out of the block, so this time I've just chosen to call it water instead of a glass block. So I've got a light ray here that is coming out of this swimming pool maybe and into the air. So again, I've drawn my normal, and this time my angle of incidence is still on my left hand side, but it's inside the more optically dense material because I'm going from something more dense to something less dense. So this is my angle of incidence. So the ray comes out over here, so here is my angle of refraction. Again, I can do it at different angles and we still get the same basic idea. But this time, because I'm going from more dense to less dense, the light ray is moving away from the normal, so that means that my angle of refraction is now bigger than my angle of incidence. So we just need to remember which way the light ray is going to move, depending on the type of material we're going from. Now I've just been saying less dense, more dense, which is a bit vague. We don't like vague. What we prefer is to be able to put specifics on things. And the specifics that tells me about the way that light travels through a material is the refractive index, which is given the symbol n. And this is basically the ratio of the wave speeds between two materials. So the refractive index of a substance is equal to the speed of light in the first region divided by the speed of light in the second region. So give you some examples. So this is when we measure it with respect to vacuum, which is pretty much what we always do. If you quoted an n value, it will have been with respect to the vacuum. So vacuum is going to have an n value of 1, because it should. Air is going to be 1.000293, so basically we say 1, which is, from that ratio you can see why we're kind of okay using 3 times 10 to the 8 for the speed of light in air as well as vacuum. It's very insignificant difference. Ice would be 1.31, water 1.33, alcohol 1.36, glass, depending on the sort, but 1.5, diamond 2.4. So it gives you an idea of the kind of range we're looking at with these n values. So now that we've got a way of talking about the n value for a material, so we've got a numerical value for the density, this will allow us to calculate exactly how the angles are going to change. So all I've got here is I've got a light ray incident on a material, it's then getting refracted inside the material. N1 is the refractive index of the material on the outside, and 2 is refractive index of the material on the inside. Theta 1 in this instance is going to be my angle of incidence, and the ones match, as you can see, because it's the angle from before. Then I've got theta 2, which is going to be my angle of refraction, which goes along with N2. So basically, what I'm saying is when my light ray goes from material N1 to material N2, I find this relationship. So N1 times the sine of theta 1 is equal to N2 times sine of theta 2. Or another way of thinking about it is that n sine of theta will always equal a constant. And this can be useful. So if I know the angle at which I shine it in at, I know the n value of both materials, I can then predict what the angle of refraction will be. Okay, so just to clarify what those were, so theta 1 is the angle of incidence, and theta 2 is the angle of refraction, just in case you didn't catch that. So that's refraction, that's the equation that goes along with it, and hopefully, like I said, that was just a recap, and it's now all a little bit fresher in your mind. We'll do a fair bit of practice at this, and we'll probably get some ray boxes out and do some actual practical playing with light as well. Okay, so remember, if you have any questions, just ask when you see me in class.